welcome to today's webinar on efficiency testing on electrical drivetrains. Your microphone will stay muted throughout the presentation in order to avoid feedback. If you have questions, we will address them at the end of the presentation using the Q&A feature of WebEx. However, you're welcome to type in questions at any time. Our presenter this afternoon is Mike Hoyer. Mike has a Bachelor's of Science degree in Electrical Engineering from New York Institute of Technology. He has over 24 years of applications engineering experience, providing solution-oriented results to customers worldwide via email, phone, WebEx, training seminars, trade shows, online videos, white papers, and on-site demonstrations. Mike, it's all yours.
Well, thanks, Krista. Hi, I'm Mike Hoyer, Applications Engineer for HBM Test and Measurement, and I'd like to welcome you to our webinar entitled Efficiency Testing on Electrical Drivetrains. We call it edrive for short, and we're going to talk about how to greatly improve efficiency measurements through continuous and synchronous acquisition of electrical and mechanical power. Now, this can be done on a variety of drivetrains, including automotive for vehicle drivetrains, and even in aerospace for power generation from a turbine. Interesting to note, at the top of this page, you'll see the first electric vehicle from 1898, a Porsche with in-wheel electric motors, weighed 2,200 pounds, had 904 pounds in batteries, and a range of 31 miles, and a top speed of 31 miles per hour. So that's quite innovative even for back then. So why efficiency testing? Well, improving efficiency is going to provide a significant growth and improvement in electrical vehicles, primarily in the distance a vehicle can travel, and aircraft power systems are going to see a great optimization of energy in their entire airplane, since that's pretty much the trend in aircraft is trying to make all the systems electrical. So how can we increase efficiency? Well, traditional testing methods and equipment have reached their limitations for improving efficiency. So new testing methods and equipment are required to significantly improve the efficiency. So in this webinar, we're going to review the traditional efficiency methods that are used, introduce some new testing methods and equipment to greatly improve efficiency testing, and then present ways to measure high voltages, currents, torque, and speed, and then show the calculations and even take a look at some waveforms for electrical and mechanical power and efficiency. So to start off, we'll take a quick look here of the various concepts for electrical and hybrid cars. We've got the conventional vehicle, parallel hybrid, plug-in hybrid, serial hybrid, battery electrical vehicle, and so on and so forth. Now, all concepts have something in common. Besides the typical mechanical components, we now have the electrical components integrated. So this creates new requirements for test and measurement. So here's a simplified electrical drivetrain. From left to right, we have the battery or batteries, a frequency inverter, electrical motor with a transmission, and the vehicle chassis with 2 or 4 driven vehicles. So electrically operated vehicles have existed for quite some time. However, it's the range that's the biggest limiting factor. And so there are 3 factors to improve the range. Well, you can first try and reduce the weight of the vehicle, but there are some limitations there, both technological and psychological. Sitting in a few hundred-pound vehicle with a large wing or a several-ton vehicle near you can be quite intimidating, and often a heavier vehicle feels safer. Now, improving battery technology, however, well, we're quite close to the physical limits of the technology already. So really, it's improving the efficiency that's going to make some great strides, because currently the efficiency of electrical drive motors in vehicles is at 50 to 60% battery to road, and this is an area for some great improvement. So why is the efficiency low? Well, a good industrial motor like an elevator has over 90% efficiency, because the elevator has a very controlled use. It's a rather simple example compared to a car. For example, you have input voltage is quite constant from the power utility. the acceleration is controlled, braking is controlled, the distance is pre-programmed, and the temperature range is controlled. So pretty much the controller for an elevator is very efficient and rather simple compared to a car. Because in a car, there are numerous uncontrolled variables, like the battery may be low or fully charged, the driver may be aggressive or a lightfoot, there might be many random braking cycles, the car might be going up or down a hill, and the outside temperature might be cold or hot. So the use of an electrical motor in a car is very complex compared to the electrical use in an industrial application. That's why today's controllers have low efficiency. So intelligence in the controller or frequency inverter needs some great improvement. So the question is, how does a controller or frequency inverter react to all these changes? Well, in order to optimize the frequency inverter, we need to record the input and the output of the inverter and correlate these electrical signals with the mechanical signals, for example, the output of the torque. Here's a simplified example of an electrical drivetrain for an aircraft. It's an auxiliary power unit, for example, very similar to the automobile drivetrain, except the drive is in the opposite direction. So starting from the right, you have the turbine followed by the generator, then the frequency converter, and then the power distribution. Now again, to improve and optimize the system, you need better technology generators, converters, and turbines. However, higher efficiency is also a significant solution. Actually, measuring the efficiency can help improve many of the drivetrain components and the way they're interconnected. So whether we're talking about an automotive or aerospace drivetrain, the voltages, currents, torque, and speed to be measured are quite similar. So for simplicity, we'll stick to the one automotive example. So starting on the left, at the input to the inverter, there are battery voltages up to 1,000 volts and currents up to 300 amps. At the output of the inverter are pulse width modulated voltages up to plus minus 500 volts, often in 3 phases, sometimes more, and currents up to 500 amps. Now, using a torque transducer or torque sensor, or sometimes known as a torque meter, we can record the electrical motor output, which includes torque and speed. Now, measuring each of these voltages and currents individually allows us to calculate the electrical power from the batteries, the electrical power from the inverter, and the mechanical power from the motor. So if we calculate these ratios, each of these sections will give us, for example, efficiency of the frequency inverter, and then we have the efficiency of the electrical motor, and we also have the final solution here, which we're targeting, the efficiency of the entire electrical drive. Now, currently, all the signals we just mentioned are traditionally measured with this type of setup you see here. We have the battery voltage, which changes slowly, so maybe a digital multimeter is used, maybe writing down some of the numbers seen. The output of the frequency inverter is often measured with a power analyzer, and in order to see the signal, sometimes a scope is used. And to measure the motor output, a torque transducer and some type of data acquisition system is used. Now, unfortunately, there are many problems with this type of setup. Number one, there's no time sync between all the recording systems. So it's difficult or nearly impossible to make comparisons between torque and electrical signals at the same time point. Possibly one reason for today's low efficiency in electrical drives is due to the inability to correlate the correct points in time between mechanical power and electrical power. Therefore, the data that is being compared is probably out of sync. Number two, when data is stored in 3 different systems, the question becomes how do you merge the data between all the systems? Number 3, no continuous data is recorded, which is needed when the results seem incorrect. And you need to do some detailed analysis. Number 4, power calculations are slow at a maximum of 20 readings per second, and that's because power analyzers are designed for static measurements, not dynamic applications like edrive. And number 5, power analyzers, they don't provide any documentation on how the calculations are performed. So even though you know the results may be wrong, maybe you get an efficiency larger than 1, you can't determine why because there's no documentation on the algorithms. So because of those problems, we sometimes hear from users that actually are trying to perform this type of measurement will say, well, sometimes we measure efficiency larger than 1, but we can't believe that because that's impossible, but we can't analyze further because we have no raw data. Here's a diagram showing a typical wired setup. Digital multimeters are used to measure the battery voltage, power analyzers measuring the three-phase voltage and currents. Maybe a scope is used if you want to see the signals as they occur. And a small data acquisition system is used to measure the torque and speed of the electrical motor. So if you were to make a wish list on how to improve on this type of measurement, it would probably look something like this. Starting off, we would like a simple system configuration, ideally one system for all different signals. That will give us one data format for all the acquired data. We want to be able to record all the data simultaneously, simultaneous measurement of electrical and mechanical power signals. And we don't want any phase shift, which can often be caused by different data acquisition systems. And we'd like faster and better results. Shorter analysis cycles. It's best if we perform the analysis for every half cycle. We'd like to have documented traceable algorithms and continuous storage of raw data so we can examine it much closer. Well, there are several ways to make current measurements. Each has its pluses and minuses. Here we start off with current shunt, essentially measuring the voltage drop across a shunt resistor. It provides high accuracy and high bandwidth. However, you've got a small voltage output, maybe only a few millivolts, on a high potential, which makes things rather difficult to measure, and they're also difficult to install. Current transformers basically are large currents are transformed to smaller currents converted to voltage. They also provide high accuracy and high bandwidth, but they're also difficult to install. They require signal adaptation. Basically, most of them have a current output which needs to be converted from milliamps to volts, so you need a conversion amp. On the other hand, you have current clamps. There are various technologies, one of them being Hall effect. Basically, large currents are converted to smaller voltages. They do have low accuracy and limited bandwidth, but they're much easier to use and have a voltage output and have a lower cost. Now we take a look at the voltages. There are several requirements and challenges for measuring high voltages. It's highly recommended that you have high voltage isolation. You'll need a 1,000 volt peak measurement range. You'd need some high bandwidth and a high sample rate, ideally 1 megasamples or higher. And you'll need an isolation amplifier or probe, but then there's a question on accuracy, since that adds more inaccuracy in your data collection. One note I'd like to make is that true RMS measurements require cycle math. However, it can be difficult to do cycle or zero crossing detection in the voltage signals due to the noisy pulse width modulated signals containing lots of zero crossings. Now, there are also several methods to connect to high voltages. In each of these methods has their challenges. Phase to phase, basically 3 voltages are measured between 2 phases. There's no control over false currents in case of problems, like a short circuit. It's a common method, but it has disadvantages in analysis. The power calculated per channel is not a real physical entity, and it needs to be constructed via some math analysis. Phase to star, again, 3 voltages are measured between phase and a star point from the electric motor, not ground. This is a rare method, as the real star point is not often available. The phase to artificial star is a much more common method. You have 3 voltages are measured directly against a virtual star point. An artificial star is created by a resistor network. However, you have to have a star adapter in order to perform this measurement. Regardless of which method you use, HBM offers solutions for all three methods. Now, HBM offers a plug-on artificial neutral module enabling convenient measurements of three-phase voltages by creating a virtual neutral or star. In fact, this module also conveniently fits into the new HBM Genesis 1 kV isolated data acquisition card, enabling direct connection to high voltage signals without having to add additional inaccuracies from probes or any other voltage divider. Now, the 1 kV board is also a great solution for measuring currents. Taking a look at some of the specifications of the isolated 1 kV input card, it has 6 isolated 4mm safety banana plug inputs, a wide input range from plus minus 20 millivolts to plus minus 1,000 volts. So you got a 2 kV span that's possible all in one card. You can use the high span for phase-to-phase measurements and the low span for shunt measurements. So quite a nice input range, all in one card. Sample rates are available up to 2 million samples per second on every channel, up to 18-bit resolution. Isolation is 1,000 volts RMS channel chassis earth, and you have an accuracy of better than 0.1% NSE of the full-scale range. And NSE is a specification called maximum static error. It's an IEEE 1057 standard, which is essentially the worst case combination of gain error, offset error, and static interlinearity error over the specified temperature range. It replaces the misused term accuracy, which often only includes gain error. Now, many of these specifications on this card were specified by the aerospace industry, so this card will meet or exceed the aerospace industry requirements for making power measurements in aircraft systems. Now, to measure the torque and speed, a high accuracy and high dynamic range torque transducer should be used, and the HBM T12 is one such torque transducer, offers maximum accuracy, safety, flexibility, and efficiency. Now, a torque transducer will acquire the torque, and sometimes you can select an option to acquire as well the speed. Now, the mechanical power delivered at the drive shaft is computed as the mechanical power is equal to 2 times pi times speed times torque, and often in Newton meters per second. So here is an example of a complete solution with many advantages using a single instrument to record all the signals continuously and synchronously. You can store all data in one system in the same file format, perform power calculations per half cycle, display all the recorded signals live, safely, and conveniently from your control room. You can actually see the waveforms on the display in your control room, and that's achieved with an optical Ethernet network cable that provides you isolation, eliminating any high voltages from entering the control room. So here's a wired setup. One system acquiring and displaying the battery voltage current, the input to the inverter, the three-phase pulse width modulated voltages and currents, the output from the inverter, plus the torque and speed are acquired from the electric motor, again, all synchronously and continuously acquired into one data acquisition system. Here's one example of a total solution using an HBM Genesis Gen 2i recorder to record all the signals, and an HBM T12 torque transducer. HBM offers a variety of systems, portable, rack mount, etc. So depending on your needs, there's a solution available. Now here's an example of some of the typical recorded signals. We can see that recording the signals continuously and synchronously allows us to closely analyze the data and study the correlations of the electrical signals with the mechanical signals. It's an important part of this whole efficiency testing webinar. So at the top half of this page, we see a 50-second recording of an RPM signal in green, a torque signal in red, Plus, just below that, we see a current in red and a voltage in blue. And the bottom half expanded view shows about 4 seconds of the current and voltage. And the bottom right half expanded view shows about 50 milliseconds of the current and voltage. Here are some of the signals and math equations used to make power calculations. Voltage normally defined as U, current I, torque N sub D, and speed is N. So a simplified power calculation for true power would equal the mean per cycle of U times I. Apparent power, known as S, would be the RMS per cycle of U times the RMS cycle of I. And mechanical power would be 2 times pi times N times M sub D. And then finally we get the efficiency calculation of the electrical motor, lambda equaling the mechanical power divided by the electrical power. Now to properly calculate the true RMS of the voltages and currents, we need to identify the cycles or zero crossings, which can be difficult to find with noisy signals like current. However, using advanced algorithms, they can easily be detected and displayed. In fact, in this pictured example, the HBM perception software has detected all the zero crossings in the phase 1 green current waveform and displayed the detected zero crossings for visual verification as seen in the red waveform. Here we see some examples of how calculations are made within the HBM perception software. For example, we start off with mechanical power, and all of these equations you see here on the screen. The green are comments, and in between are the equations. We have 2 pi times mechanical RPM divided by 60, so we're measuring in the proper units times mechanical torque. For RMS, per phase and cycle, we have the cycle RMS, which is the current and the phase 1, 2, and 3. And we're using the phase 1 current cycle detect for the measurement of each of the 3 phases of current and for each of the 3 phases of voltage when we perform the RMS cycle of voltage. Then we have the apparent power, multiplication of RMS values of current and voltage per phase, and the total apparent power is the sum of all 3 phases. Here's a picture of some of the computed waveform results, including mechanical power at the top, and the total apparent power S in the middle, and the total active power on the bottom over time. In fact, in this example, it's over a 50-second time frame, and now having these results displayed over time compared with the raw data enables further analysis of the inverter characteristics. Here we see an example of even a more complex situation. In fact, there are some inverters that change both their switching frequency and pulse width. On the top half of this display, we have 1 phase of voltage in pink and 1 current in green, both unexpanded and expanded views. Then on the bottom half of the display, we have a FFT. Actually, on the bottom right is an expanded view of the FFT centered around 10 kilohertz, showing the 2 distinct frequencies from the inverter. One peak is just below, and one is just above the 10 kilohertz mark. Here's a sample demonstration setup which we display at some various trade shows and conferences. It includes a power inverter controlling an electrical motor, which is connected to a torque transducer with a bicycle brake system to simulate a load. All the voltage and current, torque, and speed signals are connected to one HBM Genesis Gen 5i data acquisition system in this picture you see on the right, with the results displayed on the screen. Here's another setup example. This is an actual test cell at the University of Darmstadt, about 30 minutes south of Frankfurt, Germany. They use current transformers, active differential probes, an HBM Gen 7T, T10 torque transducer, and they are testing a hybrid motor. So in summary, the key to significantly improve efficiency testing is to improve, which allows you to even improve electrical motors drives, You have to collect high voltages, currents, torque, and speed continuously for detailed analysis and result verification, and simultaneously to correlate signals using a single system. These are the two key aspects of this webinar, continuously and simultaneously. You also need to record at high sample rates and high resolution due to inverter switching frequencies. Plus, all the analysis, including the power calculations, should be done per half cycle. Now, HBM offers Genesis data acquisition systems that can connect to all signals directly, display the signals live, acquire the data continuously and simultaneously, record at high sample rates and high resolution, and perform the analysis per half cycle. We've got lots of additional information available at our website, hbm.com/edrive testing. Now, on this specific page, you're going to find articles such as efficiency enhancement for the drive of the future, plus the 7 misconceptions about the testing of electric motors. You can also obtain brochures and data sheets on the Genesis high-speed platforms and the torque transducer T12. And of course, if you ever have any technical questions, you're always welcome to send us an email to our technical support group at support@usa.hbm.com or call toll-free 1-800-578-4260.